All right, we are live.
All right, amazing. Okay, so for our last day in this boot camp, we have it's gonna be a long day. We have two speakers, and our first one is gonna be William. So, William works as a performance engineer at Anthropic. He is currently on leave from a PhD program at MIT, where his research focused on making LLMs more efficient through kernel optimizations and model architecture improvements. Last fall, William helped create and teach MIT's first ever class on accelerated computing, where he led design of its CUDA-based programming assignments. Take it away,
Yeah,
William.
thanks for the introduction. Hi, everyone. So today I want to talk about sort of some like really fundamental aspects of GPU programming and trying to talk about sort of what it takes to build a really strong foundation for conceptual understanding of how to program GPUs. So who's this talk for? So my understanding is that the audience here is kind of a mix of people that are more on the system side and people that are more on the machine learning side, and I imagine that some of the folks on the machine learning side maybe are like hopeful or curious about writing kernels in the future, but are like still kind of trying to learn how to do it. And so I think the real like intended audience of this talk is like anyone who like either like intends to write a kernel soon or like might want to write a kernel at some point, but you're like still trying to build the like foundations of your understanding. And for those of you in the audience who are a lot more experienced, I think a lot of this might seem more basic to you, but I hope it still helps you see things at least like a little bit differently than you maybe thought about them before, or gives you like just like some slight like additional clarity. And since I'm going to be talking about basically how to think about the performance of GPU hardware, this really applies to any language whatsoever that you use to program GPUs. So whether you're writing kernels sort of directly in CUDA, or whether you're using some kind of higher level DSL like Triton or NVIDIA's new Cutlass 4, all of these same principles apply because they're the principles of the underlying platform that you're running on. So who am I? I think you've already heard a little bit about this, but but before grad school, I spent a bit of time at NVIDIA working on deep learning compilers there, and then got like halfway through a PhD at MIT, working on LM efficiency research, and I think one of the highlights for me was helping co-create this class on GPU programming, and I'm currently at Anthropic working on making Claude faster and more efficient. And the content for this talk is mostly adapted from essentially the first 2 weeks worth of lessons, and or some of the highlights from the first 2 weeks worth of lessons in MIT's 6S894, the course that I worked on last fall. And so this course, I co-created it with my advisor, Jonathan Macon Kelly, and with another PhD student, Nikita Lazarov. And the materials for this are all online. And if you're like if you end up being like at all interested in the material of this talk and want to like learn more or dive more into the details, I personally think we did a pretty good job putting together the labs for this course, and labs 1 and labs 2 are basically an extended version of the content of this talk. So yeah, recommend you check that out if you're interested. All right, so we're here to write kernels. We write kernels in, let's say, CUDA. What is a CUDA program? So if you take the programming interface of the CUDA programming language at face value, a CUDA program is a definition of some function in a C-like language, and then this like launch command, which runs many copies of that function you defined in parallel on your GPU. And so if you've like ever tried to like launch a CUDA kernel before, you probably saw that there's these 2 parameters you have to specify. You have to give it a number of so-called like thread blocks that you're going to launch, and then you say for every thread block the number of threads that it's going to run, and then somehow magically the GPU runs all these threads and all these blocks in parallel, and it does their computation, and everyone's happy. This is sort of the story that CUDA is trying to tell. So when you think about a CUDA program from sort of the software point of view, the picture you have in your head probably looks something like this. So you've got sort of this array of blocks, and then within each block you've got this array of threads, and each of these threads is a little program that's doing some work in parallel with the other threads. So let's look a little bit more about ways that this model can show up in practice, and we'll do this in terms of the sort of like performance puzzle that might come up when you're trying to actually write and profile a CUDA kernel. So suppose that we've got a kernel, it like runs reasonably fast, solves some problem for us. I don't know, it like adds 2 vectors or something. And we're currently launching it with 128 blocks of 1024 threads each, and it works well. And say that now, as an experiment, we try to tweak the number of the number of threads per block parameter. So now we say instead of every block having 1024 threads, which is actually the maximum that NVIDIA lets you have in a thread block, we say we're only going to use 256 out of the 1024 like maximum threads that we could have in a thread block. So you might imagine, and I think there was a point when I was learning CUDA programming where my expectation was that if you sort of have the ability to run 1024 threads, and you opt to only run 256 instead, then maybe you're somehow like only getting 25% utilization of the hardware, or something, and it's going to run like 4x slower. But for many kernels, if you actually try to do this, you actually try to bump down from 1024 to 256, you find that they actually run at the same speed. And so this is kind of mysterious. Like what were those like other 3/4 of the threads doing if running your program on a smaller number of threads, each doing more serial work, runs at the same speed? So we can ask, like, why do we sometimes see this phenomenon? And there's another puzzle that I think often trips people up when they're starting to write CUDA programs, which is, say we start with that same kernel again in its original configuration, but now instead of tweaking the number of threads, we're tweaking the number of thread blocks. So we say, now let's say we bump up our 128 thread blocks to 133 thread blocks. So this is not a big increase in the number of blocks. This is like a 4% increase. And so you might expect that, like, okay, we've sliced up our problem slightly differently. It's now running across a like slightly larger number of blocks, but probably this shouldn't affect performance that much, right? But if you actually run this, especially if you run it on an H100 GPU in particular, which we'll get to in a minute, you might actually find that for certain kernels it runs like 2x slower to increase the number of thread blocks by 4%. And so why does this happen? This might seem kind of mysterious. So I think the thing I'm trying to get at here, and we'll revisit those puzzles in a bit, is that this sort of like threads and blocks model of how to think about a CUDA program is, it's useful because like these are the abstractions that NVIDIA provides, and you kind of have to deal with them, and they have some benefits. But this is a very sort of incomplete view of what's actually going on from the perspective of trying to predict and reason about the performance of your program. So I think that for beginning CUDA programmers, often a better question to ask than like what is CUDA and how do I use it is what is a GPU and what can it do? And so here's a picture of a GPU from NVIDIA. And actually, this is the board, so it has like a bunch of random electronic components on it and stuff. But if you zoom in on like the actual GPU chip, this is what it looks like. And if you look at this picture, you might notice something like maybe the most conspicuous sort of visual feature of the GPU in this picture is that it's made of a bunch of tiny squares. And this, I think, is actually a like if you only have like a one-sentence description of what a GPU is, a GPU being a bunch of tiny squares, a fixed number of them, is a better mental picture to have than a GPU being like a thing that runs amorphous like a thing that runs like an amorphous blob of like blocks and thread blocks where you can like set the number of them that you have. Okay, so GPU is a bunch of tiny squares. Like, what are these tiny squares? So NVIDIA calls these things streaming multiprocessors, usually abbreviated to SMs. And how many of these do we have? We have around 100. And in this picture, there's like 144 on the die. In practice, if you like go and buy an H100 and you like ask it like how many SMs do you have, it'll tell you I have like 132 because like some of the 144 SMs here they like don't survive the manufacturing process, and so like they get disabled in software. But like for like most GPUs on the market, you'll get like within a factor of 2 or something, you'll get like around 100 SMs on your machine. And also, this entire talk is in like NVIDIA terminology. Like AMD has like similar concepts but different words for all these things. So if you try to understand an AMD processor in these terms, you might need to find some kind of like translation guide. Okay, so we've got 100 of these SMs, or these tiny squares. What is one? What's on one of these squares? Like, what can it do? One of these SMs, it's actually 4 smaller things. Unfortunately, these things, even though I think they're like one of the most important like units of organization of the hardware on a GPU, as far as I've been able to tell, they don't have a super standardized name. Some people affiliated with like the like sort of Thunderkit and Hazy Research world, I think I've heard referred to them as quadrants. Some NVIDIA documentation occasionally refers to them as partitions. In the course I taught last fall, we refer to them as warp schedulers. But they're basically these sort of 4 computing cores that you have within one SM. And so like how should you think of one of these things? Well, I think from sort of like fundamental like computer architecture principles perspective, actually the best approximation that you might be more familiar with for how to think about what a warp scheduler is that it's kind of like a CPU core. It actually has like a lot of design similarities to a CPU core, and so the biggest caveat to this is that it's a CPU core that's like really strongly specialized for running SIMD instructions, and we'll talk about that in a bit. But it really has a lot in common. But both a warp scheduler and a CPU core, they both issue a stream of instructions per sequence. So it's like on like every clock cycle, it gets an opportunity to like issue one instruction and get it to like start doing stuff on the functional units. It has a bunch of like physical like state resources that it uses to store the execution state for the like programs whose instruction streams it's running. So that means like if you've ever taken like a CPU computer architecture course, like a running program is sort of defined by like the position of the program counter telling you like which instruction you're on, and by the values of registers in the program. And so in the same way that a CPU core is tracking all that information in some like hardware state, a warp scheduler is also tracking that same information. And the warp scheduler has a bunch of functional units, which in this diagram from NVIDIA that you see on the left are kind of visualized in this stylized way, where you've got a bunch of circuits that can do like integer math and floating point math, and also in for the last several years, the thing everyone's really excited about is that it can do like matrix multiply math using some specialized hardware. And so when the warp scheduler like issues instructions, those instructions kind of like schedule onto the functional unit. So they like cause the functional units to do stuff and produce new data, which then like goes back into the register file. All right. So and I think that this analogy like really is quite close. Like if you look at like an AMD CPU on the left, and you look at like an NVIDIA GPU on the right, it's the same basic design where you've just got this like sea of cores, and each core has like a register file. It has some control. It has some functional units. And maybe the most conspicuous difference is that on the GPU you've got this extra level of hierarchy, which is the SM, which is grouping for warp schedulers together. And in this talk, we're actually not going to talk that much about why that SM level of organization exists, but the short answer is that it exists. It exists because that's the level at which memories or resources are shared. And we can talk about that more during the Q&A if people are interested. All right. So that thing at the bottom of the screen should have animated later. But so at this point, maybe if you have a bit of experience with CUDA, or if you're like thinking about how this relates to the previous slides, you might be starting to get a bit of uncomfortable. It might seem like there's some dissonance here because it kind of seems like the math doesn't check out on everything I just said. So like as we talked about earlier, like when you're launching a kernel, you might like very typically launch a CUDA kernel with up to like hundreds of thousands of threads. Like the kernel launch we were looking at earlier, like it's launching like 128 blocks. Each has like 1K threads. That works out to like 131,000 threads that we're launching. But we just said that a GPU physically, it only has hundreds of warp schedulers. And we're claiming like each warp scheduler is like a CPU core. Like if you multiply out the like 132 SMs on an H100 by 4 warp schedulers per SM, you get around like 500 warp schedulers. So what gives? Like how can we be running hundreds of thousands of threads in parallel if we only have like a factor of 1,000 fewer warp schedulers? And so there's actually 3 answers to this, so that also should have animated later. So one answer to this is that a warp scheduler, every time it issues an instruction, is not issuing that instruction in a way that serves only one thread. Warp schedulers, as I mentioned a bit earlier, they're like a CPU that's been optimized for running SIMD instructions, single instruction multiple data instructions, where you're basically operating on a whole vector of data at a time. And so what the hardware is actually doing is it's sort of like grouping the data for like 32 consecutive threads together into a big vector, like physically this is what's happening in the hardware, and the warp scheduler, every time it issues one instruction, that instruction is going to do a sort of 32 threads worth of work across 32 sort of lanes of this vector. And the other thing that lets us run more threads than we have, the other thing that lets us run more threads than we have warp schedulers on which to run them, or even more than a factor of 32 more than we have warp schedulers to run them, is that a warp scheduler it's not restricted to just running 32 threads worth of compute at a time. Even though a warp scheduler on any given cycle, it can only issue an instruction for 32 threads. It can like time slice different groups of threads together. So on one instruction it might be, or on one cycle it might be issuing an instruction for some group of 32 threads, and then on the next cycle it's issuing an instruction for a different group of 32 threads. And so this means you can have more than 32 threads with their sort of state resident on a warp scheduler at any given time. And finally, if you ask CUDA for like a huge number of blocks, if you ask it to spawn like thousands and thousands of thread blocks, it won't like crash. It'll instead like run those thread blocks like serially one after another on various SMs of the GPU. So actually, I think I have a few more slides to like elaborate on exactly what all these pieces mean, but I think now would probably be a good time to interrupt your questions and go back and explain anything that people found wasn't clear.
I think there aren't any. There are some comments in the chat, but no specific questions on what was going on here.
Okay.
Never mind.
Any comments? Does anyone want to tell me I'm wrong about something?
There are now things pouring in. Okay. So Vikram asks, could you explain the relationship from threads to blocks?
Yeah. So at the soft. I think first sort of important to flag that like both blocks and threads, they're like fundamentally software abstractions. The hardware is not structured in terms of blocks and threads. So I guess with that said, to a first approximation, you can think of a CUDA kernel as just saying, I want to run a certain total number of threads, and I want you to basically slice those threads up into groups of 32, and those groups of 32 are called warps, which is why the thing is called a warp scheduler. And then I want you to like map those warps onto the various warp schedulers of the machine and start running them as fast as you can. However, there is this extra level of organization where you say, in addition to having sort of a certain total number of threads, we're also going to say that we're going to group these threads together into these larger units called blocks. So it might be that we're saying like we want to have like 131,000 total threads, but each like 1024 consecutive threads we're going to say like belong to the same block. And so what are the consequences of this? Why do we care that 1024 of our threads belong to the same block as opposed to different blocks? So we're not going to get like super deep into this in this talk, but the answer is basically that threads on the same block, they can communicate with each other very efficiently through a shared memory scratchpad, shared in the sense of shared between threads within a block, and they can also synchronize with each other, which is kind of necessary to make the communication work. And so this means you can do interesting things that you can create like consumer producer queue relationships where like some warps are like writing into a queue that's stored in the shared memory scratchpad, and then other warps are like popping things out of that queue that's stored in the shared memory scratchpad, and they're synchronizing all of this using semaphores or something. And so that's why we care about blocks. They're sort of they're the unit of efficient cooperation between threads. I hopefully that answers the question.
Yep. Another question was, how do I ask? Okay, basically they're asking like, does the warp scheduler have 32 cores to process 32 independent execution contexts, or is it different?
Great question. So it depends what you mean by a core. So the kind of unsatisfying answer is that like some things you have like 32 copies of them, or like some large number of copies of them, depending on exactly how the hardware is tuned. And like some things you like essentially only have one of. So what do you only have one of? The most conspicuous thing you only have one of is like the sort of like instruction decode and issue logic that can decode and issue one instruction per cycle, and so that means that it is like physically impossible for the warp scheduler hardware to issue like 32 different instructions for 32 different threads on one cycle. It just can't do it. What it can do is issue one instruction that does like the same math operation, say, on 32 independent units of data. So it might be that it issues like one add instruction, and then that add instruction is going to pull it's going to pull like 32 left-hand side like scalar operands from the register file, and then like 32 right-hand side scalar operands from the register file, and then it's going to add those element-wise, and then put the 32 results back in the register file. And then a natural question that you can then ask here, especially if you're familiar with the way that CUDA code actually looks, is what if I try to get the threads to do different things? What if I have like an if statement that says like if my thread index is even, then I do this, and if my thread index is odd, then I do this other thing. And the short answer is that the hardware is basically going to use masking to do to like make sure that it's only ever actually issuing like one single instruction at a time, and that those instructions are just like sort of operating on the right subset of threads for everything to work out in the end. So concretely, if I say like I want my even number of threads to do an addition and I want my odd number of threads to do a subtraction, what's going to happen is that you spend one cycle doing an addition, you spend one cycle issuing an addition that that sort of acts on half the threads. And then you spend another cycle issuing a subtraction that acts on the other half of the threads. And as you can imagine, if your threads end up doing like very different things, if like all 32 of the threads in a work are doing like 32 different things, then this is going to have like a huge performance cost because you have to you have to spend like 32 cycles issuing like 32 different instructions to service all the to make progress on all the different threads in the work. And then in terms of what state is being tracked, the register file is kind of tracking separate like state for data registers on like a per thread basis. Hopefully that
I think that I think that's a very good answer. Another question. Oh, there are more. Is why specifically the number 32, and are there trade-offs to running more or less threads as a warp at a time?
So it is a fixed design decision in the hardware, and has been for many years, that that the unit of warp scheduler like SIMD execution is 32 threads. I think this has been true basically since the first programmable NVIDIA GPUs capable of running CUDA. I think an interesting question is, like as a hardware architect designing a GPU, why would you choose 32? And I think the answer to that is not obvious. You need to have sort of like, you need to have a theory that like, here's like some corpus of programs that you want to be able to run efficiently, and then you like do a bunch of empirical analysis on like, here's the costs and benefits of choosing different warp sizes in terms of like so basically the two forces pushing in either direction here are, on the one hand, you'd like your warp granularity to be as small as possible, because that gives you as much sort of freedom to have weird control flow without incurring performance penalties as possible. So if the warp size were like 8 threads instead of 32 threads, then then it would be then you could have like different groups of 8 threads all doing different things at a time with no performance penalty. Whereas if you try to do that on actual NVIDIA hardware, you'd end up incurring like a factor 4 like instruction issue like performance penalty, because you'd have to spend 4 cycles issuing 4 different instructions for the 4 different groups of 8 threads in your work. On the other hand, from an actual like physical like circuit design perspective, the control logic associated with like issuing instructions and tracking dependencies between them and so on, that is expensive. And that uses area on the chip, and it uses power. And so the more threads you have in a warp, the more bang for your buck you get on that control logic. The more data you can process per sort of unit of control logic cost spent. And these two things together like create some kind of U-shaped curve that where like there's like where like NVIDIA believes the minimum of some kind of expected cost measure is at 32.
In interest of time, I will just ask 2 more questions. We can circle back to anything later. One question was basically the term scheduler implies some kind of scheduling of a component. And they're asking like, what is the lowest level of component that is like directly used for operations or computation on the GPU?
I'm not sure I entirely understand the question. What does asking for like the lowest level of component mean?
My guess is they mean like, what is the hardware component that is actually being run? But I'm not sure. Yeah.
Yeah. So like the yeah, if you mean lowest level in terms of like levels of abstraction, like the warp scheduler, it's like a physical thing that exists on the chip. So in a sense, it's like as low as you can get, in that like there's there's sort of no there's like no illusions like intervening between you and the warp scheduler. Like there really is, like if you could like look at it with a microscope, there like really is actually a like little like 1/4 of one of those little squares is like one warp scheduler, and it's running your code. I think there's also separately this question about scheduling, and yeah, and I think I'm also like not, I'm like maybe not entirely sure what's being asked there either, but something that like might answer your question. If your question is basically like what concretely what kind of scheduling is actually going on, the sense in which the warp scheduler is doing scheduling is that it's basically keeping track of dependencies among instructions, and it's only ever, and it's basically trying to issue instructions as soon as their dependencies are ready or available. So for example, if I try to issue like an add instruction and then another add instruction that depends on that add instruction, I believe on most, if not all, NVIDIA GPUs, an add instruction has a latency of 4 cycles. So basically, the warp scheduler is going to like issue the first add instruction, and then sort of like try to run the next add instruction, but then find that it can't because like 4 cycles have not yet elapsed that would like supply the data that the second add instruction depends on as its input. And so the warp scheduler will instead sort of make sure that the second add instruction only gets run after the after the first one's output is guaranteed to be available. And it can make these scheduling decisions in fairly sophisticated ways because because of this time multiplexing thing that we like mentioned in the slide, and we'll talk about a bit in a few more slides. The warp scheduler is actually sort of like juggling like multiple warps worth of instruction streams at a time, and like while one is unable to make progress, it'll like try to schedule instructions from the other ones, and this lets you sort of keep the hardware at high utilization. So that I hope that at least gives a flavor of the kind of concretely the kind of scheduling that's going on inside this thing, and I hope that at least partially answers your question.
And then the last one before you can move on is just a follow up from the thread divergence example. They're basically asking like if you have that branching case, is the throughput of the scheduler cut in half?
Essentially, yes. Yeah, like if your even numbered threads are all trying to do one thing and your odd numbered threads are all trying to do another thing, then you're getting sort of only like 16 threads worth of work done per instruction instead of 32 threads worth of work done, and so it is basically gonna cut your like instruction issue throughput per thread in half.
Okay, thank you so much. I will let you continue, and yeah, feel free to keep asking more questions in the chat, and we'll get to them. Cool,
great. All right, so I guess just elaborating on some of the things that were on the previous slide. So what concretely do we mean when we say that the warp scheduler is running these like SIMD instructions? So I imagine some of you might have at some point, maybe in like a C programming class or something, if nowhere else, encountered this idea that on like pretty much all like medium to high end modern CPUs, you have these like kind of obscure but like very powerful instructions available called SIMD instructions that typically they do like math operations or like other like simple like integer logical ops or things like that. But with a twist that instead of operating on just like one or like a few scalar values at a time, they operate on these wider vector registers that let you process like many elements in parallel. So like this is sort of pseudocode. This is like not a real SIMD API that exists as far as I know. But you can imagine that if you're like writing a C program that's trying to write that's trying to do like SIMD operations, you're like you're making these variables that whose data type is like is like vector of 16 32-bit floating point numbers or something like that, instead of doing the sort of more naive thing of operating on data types which are like a single 32-bit floating point number. And then you have these like special instructions that operate on these vectors and will do things like do like 16 addition operations at a time. If you like explicitly use the API in this way. And on CPUs, this is very powerful because you can just get like much better like arithmetic throughput if you use these instructions that do many things at once than if you insist on like doing everything in terms of individual scalars. And this is like exactly the same at the hardware implementation level. This is exactly the same trick that's being used to execute all GPU code, basically. So the like underlying like physical design constraint reasons for why you'd want to build this feature into your chip are the same between CPUs and GPUs. The only real difference between what the GPU is doing and what the CPU is doing when it runs SIMD instructions is that for one thing, the GPU can kind of only run SIMD instructions. It's like the instruction set just doesn't have any non-SIMD instructions. And for another thing, the way that this is exposed to at the software level is different. So if you've like ever written CUDA code, you know that like conceptually what you're doing is you're writing a program that describes the behavior of a single thread. But we just said that like single threads don't actually have their sort of own independent control logic, and instead it's like 32 threads at a time, sort of all step together and execute the same instructions. And so if you want to have an accurate mental model of what the hardware is doing, you kind of need to translate the code on the right here in your head when you see it in a CUDA program into the code on the left. Or I mean, you'd have to replace the 16 by 32 because that's how the GPU is tuned. But conceptually, writing what looks like the sequence of like scalar operations here is actually like physically going to cause the GPU to do like 32 scalar operations in parallel on like 32 independent copies of this program that you wrote. So this means that you kind of have to take this perspective shift of like when you're reading CUDA code, like not really taking it at face value as having the performance that you'd expect of like a C program that looked the same. You really kind of have to in your head think like the processor and imagine how every group of 32 consecutive threads is going to step together. All right. We also talked about how the warp scheduler time multiplexes between different threads. So this is, I think, actually maybe in my experience as someone who like learned CUDA a few years ago and also like teaching this course, I think this is actually maybe one of the like hardest and most subtle points to grasp in really understanding the sort of like performance, like the mental model that you need to have to reason about the performance of GPUs. The kind of key idea here is that a warp scheduler can be tracking state for more than 32 threads at a time. Like even though the warp scheduler on any given cycle, it can only issue an instruction for like 32 consecutive threads in a warp. It can even on that same cycle still have some like register state sitting around and some like program counter sitting around for threads that it is not issuing an instruction for on that cycle. And the reason that the hardware has this, and what the warp scheduler will do is it will it will like somehow try to juggle these like multiple warps worth of instructions that it needs to issue. So it'll run like instruction from one thread from one warp, and then like an instruction for another warp, and then an instruction for the first warp again. I think up to actually like quite high numbers of warps. I think the maximum number on most GPUs, if I recall correctly, is like 8 warps at a time that it can be like juggling in instruction streams for. And so like why can the hardware do this? Like it's not actually obvious to me, or it wasn't obvious to me when I first learned about this. Why it's beneficial to have this feature as opposed to just doing everything within a single warp if the instruction issue throughput is the same. And basically the reason is that within a single warp, you might have like dependency chains among instructions that mean that you would need to be spending some time stalled while executing that instruction stream, right? So say you have an instruction where after you issue it, the results aren't available like immediately on the next cycle. You instead need to wait wait an extra cycle, say, before the results are ready and any dependent instructions can execute. So if the pattern of instructions that you're running within a single thread or a single warp has this kind of like long serial dependency structure to it, then running just one warp is going to leave the warp scheduler stalled for like potentially like very large fractions of its runtime. But if you have other independent warps that can whose instructions can go and like fill in the gaps, then then you can recover the sort of full throughput of the hardware. And so if you as the programmer know that you have a bunch of independent work to do, like you have like some like many million element vector, and you want to do some independent operation on every element of that vector or something, then you can map different units of that work onto different warps, and then the warp scheduler will use work from warps that are ready to make progress to fill in the gaps in the schedules for warps that are not yet ready to make progress. And I think an important sort of piece of the picture to keep in mind for this is that you also have this sort of finite pool of functional units, and the functional units do things like it's like a bunch of circuits that are like floating point multipliers and adders and like integer bit shift circuits and like interfaces that like talk to main memory to do like loads and stores and a bunch of stuff like that. And different types of functional units have different are like spec for different throughputs and have different limits on like how many instructions they can be like helping execute at a time. So I think it is the case, for example, that like 32-bit floating point addition on an NVIDIA GPU, I think you can basically issue a floating like a 32-bit float like addition instruction on like every cycle, and you will like never overwhelm the like floating point adder units. But there are other instructions like for example I'm pretty sure like 64-bit floating point addition that the SM is provisioned with many fewer resources for. And so if you have like independent warps that are like all trying to run like 64-bit floating point addition instructions, they're going to interfere with each other from a performance perspective. Like they're all sort of contending for this one scarce resource, which is the like 64-bit floating point functional units, and they'll and like having 4 warps all trying to drive the like 64-bit float adders. Like it's not going to just like magically run 4x faster than if you had like only one warp trying to do that, because you're going to hit the underlying throughput limits of these shared functional units. So like for any given workload, this actually like goes like like analyzing all this stuff goes like pretty deep and is like not trivial. And you have to like pull up low-level NVIDIA documentation and like consult tables that tell you the like throughput of like different instruction types, and like sometimes you need to like run micro benchmarks to like reverse engineer things that aren't documented in NVIDIA's docs. But I hope that at least this sort of rambling spiel gives like some flavor of the kinds of considerations that are like useful to keep in mind when you're trying to reason about the implications of this kind of time multiplexing behavior. And also, by the way, like the cores in your CPU and in your like laptop or phone or whatever, they can do this too. Typically not with this high degree of concurrency. It's commonly like just 2 threads at a time per CPU core or something. But this is also like very much a consideration in CPU performance engineering as well. All right, I think now's probably a good time to take more questions because
I actually had 2 like maybe minor questions. So one is the program counter the same for all the threads in the warp?
Yeah. So this is so the answer to this is actually pretty subtle. To a first approximation, you should kind of imagine that the answer is yes, like at least for the purposes of instruction issue. It's like for instruction issue, it's like you have some instruction that at least one thread in the warp wants to execute, and that is like identified by some program counter pointing into the program binary. And then you issue an instruction for that one value of the program counter, and the state of like which threads like are or are not like participating in that instruction, you can imagine it as being tracked by like a Boolean mask that has like stores like a bit for every thread saying like, is this thread like currently active for the instruction that we're executing. Where this gets more complicated is when you do like weird patterns of synchronization where like some of the threads in your warp try to like block on some semaphore reaching a certain value, and then like other threads in the warp need to like make progress beyond the point where there's the first set of threads blocked in order to like unblock them. And actually, like the behavior of this has changed across GPU generations, and is also like, and you also need to be like careful where like different kinds of instructions will like treat the semantics of this like somewhat differently from other instructions. So basically, the short answer is like there are edge cases where the processor actually does need to track independent program counter state per thread in order to avoid deadlocks. And if you're interested about those, then like email me after the talk, and we can.
So I guess like if you're writing in CUDA, like you wouldn't really care about this, right?
It depends what kind of synchronization you're doing. Like
okay.
There are cases where basically you can write programs that would deadlock if the hardware were not capable of tracking independent program counters per thread, but they do not in fact deadlock, and it's because the hardware can track independent program counters per thread.
I see. And then the second question is just like, are the particular like thread indices or like whatever unique identifier always grouped to the same warp? So like in this example here, like are threads 0 through 31 always grouped to the same warp?
Yes, but basically a warp. So yeah, threads have these like integer IDs, and a warp is definitionally 32 consecutive threads with the start of the interval aligned to a multiple of 32. with like consecutive integer IDs. So like the threads like 0 through 31 are like always definitionally like part of the same warp.
I see. Okay, I will ask some of the other questions in the chat. So one question is the time multiplex on the warp scheduler on the level of 4n warps in a thread block, thus in the same kernel, or about concurrent kernel launches using different contexts?
So this is all within one kernel. That's a great question. And I think from some like from some conversations I had recently with some folks, I'm led to believe that an undocumented limitation of NVIDIA's GPU hardware is that a warp scheduler can't actually run warps from multiple different kernels at the same time. So I think if you want to get this time multiplexing, you have to do it within one kernel. And I think also like another thing to keep in mind is that the 4 warp schedulers within an SM, they're actually able to do this like completely independently of each other. So you can think of each one as just like I think that they often be running programs from like the same binary, but it's like you can think of each one as its own like totally independent like core with its own control logic that that is like as independent of the other warp schedulers as like one CPU core is independent from another CPU core. And so that means that that you can get like a pretty fine granularity of interleaving here, where it's on a per warp scheduler basis and not on a per SM basis.
I see. And the last question is kind of a more general thing. What is your mental model to avoid cache misses and take care of data locality? I guess they mean in your code.
Cache misses, yeah. So I unfortunately didn't really include anything about memory in this talk because it's like a huge topic and I didn't think we'd have time. The short answer to that is that there like is no short answer and it just like depends a lot on like the particular on like the structure of the particular workload that you're trying to implement. I think like a general rule that I follow is don't try to rely on the implicit L1 cache much at all, and instead prefer to use the like explicitly addressable shared memory scratchpad in order to get like good data locality and reuse. I think that's maybe the one sort of like easily stated like generalizable transferable lesson. But short of that, it's like you just gotta think about the specific kernel you're writing and think about like what could be reused where and how. And then after you get experience with it, there's patterns that show up over time where like anything matrix multiply flavor, you find that you want to like break it into roughly square tiles and then maybe like pipeline loading of those tiles with like computing on other tiles and things like that. So there's like a bunch of patterns that show up, but I unfortunately I don't think we really have time to get into them.
Okay, yeah. I think you can move on from here. Cool.
So I think one other thing is just I think worth like explicitly pointing out about this like instruction like latency hiding and like overlapping behavior is that if your code conforms to the right patterns, you can also get the same kind of latency hiding within a single warp. And it just all depends on what sort of the dependency graph among your instructions looks like. So if you have a bunch of instructions in a straight line where each one depends on the previous one, and you have only a single warp per warp scheduler, then you're out of luck because you're just going to be like spending a lot of time stalled waiting for the previous instruction to complete so you can start the next one. Where it gets interesting is if within a single warp, your dependency graph does not look like a straight line, but rather looks like some kind of branching and reconverging like wider graph where some things can be done like independently of or like in parallel with other things. So in cases where you have like multiple like independent instructions within the one instruction stream, the warp scheduler is actually like pretty good at at sort of filling in the gaps in your own in your single warps instruction stream with other instructions from the same warp. And so this means that if you're sort of like thoughtful about it, you can actually often get away with having a like relatively small number of warps and still run the hardware at like full utilization. You just need to think about whether you're stalling the processor on sort of long serial chains of dependencies or not. And so like so a way that you can take advantage of this is you can like unroll your loops, and so maybe it's like within a single iteration of a loop body, all your dependencies are basically like serial dependencies, one after another. But maybe across like 2 iterations of your loop body, those 2 loop bodies are actually like independent of each other. And they're like operating on like disjoint elements in an array or some pattern like that. And in those cases, through a combination of like manual effort and the compiler doing its job and the warp scheduler doing its job, if you know what you're doing, you can get like interleaving and overlapping between the latencies of like different instructions belonging to like different iterations of the unrolled loop. Anyway, so this is like a somewhat more advanced class of optimizations, but I think it's important to know that like having multiple independent warps is not your only recourse if you find yourself stalled, if you find the warp scheduler getting stalled on a lot of on a lot of like serial chains of instruction dependencies. And CPUs can also do this too. CPUs, in fact, are much better at this than GPUs because they have to achieve good performance. Because CPUs have like many fewer threads and much less like independent work. And so the only way to get good throughput is to like really, really aggressively try to extract parallelism from the instructions of a single thread. All right. So I guess to recap some things and think about the implications of what we've been talking about. So I think one like useful number to have in mind when you're doing CUDA programming is how many threads do you need to keep an SM busy. And the minimum value for this you can compute is just like 4 warp schedulers on the SM times 32 like threads per warp scheduler. You needed like at least 128 threads on an SM in order for it to not have some like idle warp schedulers, basically. And then also sort of an analogous question you can ask is how many threads do you need to keep the entire GPU busy? And this is going to depend on the number of SMs on the GPU. So let's take like an H100 as an example. An H100 has like 132 SMs. And if each of those SMs needs 128 threads in order to keep it busy, then you need like around like 17,000 threads in your kernel in order to have like, in order for it to even be theoretically possible that you'll like saturate the throughput of the GPU. Again, in practice, you might want more than that because you want to exploit the time multiplexing behavior somehow. But this is kind of like a bare minimum. Yeah, so it's often better to have more warps per warp scheduler, but this is what you have to. This is the lower bound. All right, so let's return to some of those puzzles that we talked about at the very beginning of this talk. So the first puzzle we mentioned is sometimes you'll have a kernel where you can like decrease the threads from the maximum down to some like much lower value, and it like doesn't hurt performance nearly as much as you expect. And we're now like pretty well equipped to explain this from our like understanding of the hardware, which is that both of these two configurations stand a good chance of being able to saturate like 128 full SMs. And I guess one constraint I didn't mention is that all because blocks are intended as the unit of like communication through shared scratch pads in a kernel, like the threads within a block can talk to each other through a shared scratch pad. At the physical implementation level, that means that all the threads in a thread block need to live on the same SM. You can never have a thread block that crosses SMs. So like this kernel launch here, it can schedule across like at most 128 SMs. So like on an H100, it would be like guaranteed to not be using some SMs. And then within each of those SMs, it's going to try to like partition its threads among various warp schedulers. But I think this is kind of interesting that you can that because you only actually have like because you only have 4 warp schedulers, you can saturate them with 1024 threads on an SM, but you can also very plausibly saturate them with just like 256 threads is usually like pretty safe, and you can sometimes even go as low as 128. All right. And then there's one final effect we talked about for how kernels can end up running many more threads in total than you have like total like warp schedulers on the machine. And that is that if you ask CUDA to launch a kernel with a huge number of blocks, so say I ask for like 396 blocks on a GPU with 132 SMs, then the GPU is just going to schedule those blocks serially onto SMs as they become available. So here, like 396 is like exactly 3 times 132. And so if I try to launch a kernel like this, like probably what the GPU will end up deciding to do is to have each SM be responsible for running 3 blocks worth of work, one after another. And this has some implications for the second puzzle that we talked about. So the second puzzle was, why is it that if we have just this 4% increase of the number of blocks that we try to allocate in our kernel from 128 up to 133, why on say an H100 might this like tank performance and make it like 2x worse? And the reason for this is that you've crossed the threshold from having fewer blocks than SMs, so that every block can run on just a single SM, to now having one more block than you have SMs, which means there's going to be a straggler. Basically, you're going to process the first 132 of 133 blocks all in parallel with each other across your 132 SMs, and then the 133rd block is going to need to, at that point start and then run to completion on just one SM. And that single final block is going to end up sort of tying up the entire GPU if you don't have other kernels available to run until it finishes. And so the other like 131 SMs are just going to be sitting idle while that one SM processes the last block. So this is another example of how like the CUDA programming model at the software level really kind of obscures important details. It feels like this number of blocks parameter is this like continuous parameter that you can just kind of tune arbitrarily. But actually it has these like really discrete threshold effects that you can only explain by sort of thinking in detail about the actual like physical structure of the hardware. All right, and with that, there's like some other topics that I think we've actually largely addressed, and then there's like weirder features that we can like talk about if people are interested, that kind of complicate the simple model that I've been presenting in this talk. But yeah, I guess with that, I'll hand it over to the Q&A.
Perfect. Thank you so much. I'll start with I guess the chat questions, and I have a question of my own, and if people have more, we can ask, and then Simran will be coming soon, so we'll probably just cut it off when she's here. So one of the questions is basically like, how good is the CUDA compiler at interleaving instructions to maximize hardware utilization without like explicit loop unrolling or on the programmer side?
So that's a really good question. I would say it's okay. I think opinions differ on exactly how much faith you should put in it. I'm generally pretty paranoid, and I try to do things. I try to write my code in a way that leaves little room for doubt in how the compiler is going to decide to optimize it. And so like one great way to do that that's also like quite lightweight is like explicit loop unrolling, because like modern C compilers and by extension like the CUDA compiler, it is extremely easy to unroll loop. You just write one line that says like hash pragma unroll and then a number, and it unrolls your loop by that factor, like automatically inside the compiler, but in a way which is like which is guaranteed and which you have explicit control over. And so I think that there's a lot of lightweight things like that sort of take decisions out of the compiler's hands and put them in your hands, but which still get the compiler to do a lot of the grunt work for you. And I think it's good to sort of to know what those are and to seek them out and to try to leverage them as much as possible. But I think it is often the case that if you really want to have confidence in what's going on, you got to like write your program, compile it, and then look at the generated assembly either at the PTX level or at the actual like underlying hardware ISA level, which is called SAS. And sometimes things will surprise you where the compiler has made a decision that is like quite different from the decision that you would have wanted it to make.
More questions have streamed in, so I will not ask mine. I will just let them ask. So one person asks, is it possible to basically write CUDA code that explicitly maps warps to a specific SM?
That's a great question. To a first approximation, the answer is no. And this is actually this is very annoying. I think it would be a like highly desirable feature for the API to give you more explicit control over how things get mapped to particular physical SMs, but you don't actually have it. Something you can do, and this is like obscure and rarely done, but you can query which SM you ended up on when a block starts. There's like a particular like inline assembly instruction you can use that'll tell you your like physical SM ID, and so in principle you could use that to have every block sort of choose what its logical identity within the algorithm is going to be on the basis of its physical SM ID, and so you could kind of take control back into your hands that way if you wanted to. I guess it is worth saying like the reason that the APIs work the way they currently do is that different SMs are for the most part interchangeable. There's like a slight exception to that, and well, I won't get like deep into it, but like basically the SMs are to a first approximation interchangeable with each other. But the thing that I think you often want a lot of control over that CUDA also doesn't really give you good explicit control over is when different blocks are going to schedule onto different SMs. We haven't talked about memory much, but it's like an important fact about the GPU that it has an L2 cache that is shared across SMs. So if one SM tries to read data from main memory, and that data then ends up in the L2 cache, then another SM that tries to access the data shortly thereafter will be able to take advantage of the temporal locality to get a cache hit. And for a lot of kernels, this like L2 locality thing is actually incredibly important, and you like really need to write your kernel to take advantage of it to avoid any bottleneck on main memory bandwidth. But then the problem with this is that in order for the cache hit to actually happen, the the second SM needs to read that data like around the same time as the first. But you actually have no control. You have no direct control over the scheduling algorithm that's used to map blocks to SMs. So you kind of have to make like educated guesses about what is going to run when, and then like design your data access patterns around those sort of approximate theories of how the scheduling will work. And this, in my opinion, is just like a maddening way to try to program a computer. But these are the tools that NVIDIA has given us.
Sorry. So yeah, actually, they clarified that what they were specifically talking about was mapping the warp to a specific partition on the SM. That's my mistake.
Oh, to mapping a warp to a specific warp scheduler.
Yes.
I think at least most of the time this is basically done round robin. So it's like the first 4 warps go on to warp schedulers like 0 through 3 in order, and then the next 4 warps just like start again from the top and so on. I don't know. I don't know if this is like explicitly stated anywhere, but it's like overdetermined that this must be how it works because there's like a bunch of more advanced features, especially in like recent generations of GPUs, that were like the design of the API would only make sense if this were how it worked under the hood, and so it must work that way.
I see. And Simran's here, so I'll just ask one more question from the chat. They ask, how do GPUs handle scheduling and context switching, and how does this differ from a CPU's process scheduler?
Yeah, so great question. So the short answer is that there is no context switching, at least in the sense that it exists on a CPU. So like a CPU, you can have a process that like accumulates a bunch of state in like registers and in like the L1 cache, and then gets like preempted by the OS and has to like save all that state in like main memory, and then like start running some other process, and then like the registered state gets restored, and the cache, you're just like out of luck, but you like presumably repopulate it after you resume the process. On GPUs, there is no such thing. Once a thread block starts running on an SM, it is a guarantee to run to completion without being preempted or like context switched out for a different thread block. And the main reason for this is that on the GPU, and like for the most part, instead of using like an implicit L1 cache, you use this like explicit like memory scratch pad, and so you need to like in order to preserve the behavior of the code when you like context switch it out and context switch it back in, you need to save the full contents of that like explicit like local scratch pad, so that you can restore it later. And that would be like quite an expensive operation, and I think like that this would make like even harder to reason about the performance of kernels because you need to contend with the possibility of these preemptions happening. Yeah, so basically there is no context switching on the GPU. There's a sense in which you can think of the warp scheduler juggling different warps as doing something a little bit like context switching at a sort of lower level of the hierarchy, but it's really pretty different. And like CPUs do that kind of multi-threading on a single core where they get like time multiplexed as well, and like on CPUs you don't call that context switching. Like at least I don't. I would want to double check like my understanding of the like computer architecture terminology on this to know what the normal conventions are. But at least like sort of like OS preemption, context switching, and like multi-threading on a single core context switching are like very different kinds of things, and on the GPU you like only have the latter one.
All right. Well, that'll be it for William's talk. Thank you so much for coming. I think if people have more questions, they can reach out to you somewhere online. I don't know.
Yeah, actually, yeah. Can I like put my email in the chat or something?
Sure.
Yep.
Yeah.
As a as a comment, or what's the best way to do it?
Yeah.
Yes, I think you can just join the chat.
Oh, connect your YouTube
Here.
camera.
We'll remove your screen, so you can go do that. And Simran should be here now.
Hello?
Hello. So yeah, you can set up, I think you can like present somewhere and I can add it to the screen. Yes.
I think I'm gonna head out, but yeah, thank you all for the opportunity to speak. This was a lot of fun, and yeah, but I can't get into the chat, but I'll just like send you my.
You could just send it to one of us, and then we can like post it after. But thank you so much. Yeah,
Sounds
it was
good.
a really good talk.
Yeah, thanks. All right, have a great day.
So I can just screen share, Alex?
Yes, I think so. And then I can add it to like a screen layout thing. And while you're doing that, I could just give a quick intro. So I'm sure a lot of you guys already know who Simran is. But for those who don't, she's a PhD at Stanford, advised by Chris Ray. She has done a lot of really, really cool, amazing research, basically around AI capabilities and efficiency. So there's a lot of stuff that you might have heard of, like Thunder Kittens, or lolcats, or zoology and things like this. There's tons of other amazing works that I'm sure you're all aware of. So today she'll be mostly talking about Thunder Kittens, but yeah, and maybe some other research that she's been involved in. So I think.
Can you see my screen?
No, I think it's just the stream.
Just the stream. All right. Okay. Sorry about that. Stop screen. Okay. Is this good?
There's no option currently.
Present. Is that good? I'm trying. Oh, I pressed the share screen button or the present button.
You don't see anything.
Yeah, I don't see. It also might be like, yeah. Sorry, we've also been trying to figure out some stuff on here. But no, it doesn't appear on a camera right now.
I should just be clicking the share screen button on the bottom, right?
Yeah.
I think so. Yes.
Okay. Try one more time. Otherwise, I can just send you my slides.
Yeah, that also works.
Okay. No luck. It says that it's sharing my screen.
Oh, I think I see something. Oh, it just moved, but I just see GPU mode.
Maybe it's on. Nope. Yeah, no.
All right, Alex, I'll send it to you.
Yeah,
Sorry about that, folks.
Do you see like a present or invite button below or no? Like on your
I pressed the present button and I said share screen.
Oh, that's so odd.
Let me see if I do it, if it works. If it's like, can two people, like, is it because William shared or something?
Maybe. Okay, I will just send it to you very quickly.
Sure. Yeah. I guess in this time, like, for people watching, you could just kind of take a break. We know it's been kind of a long day, so yeah.
We have William's email, but for some reason it's not letting me post in the chat. Alex, can you just post it quickly?
Yes.
I put it in our Slack.
Okay. Yeah.
I just sent it to you on Slack, Alex.
Okay. Thank you. Okay, I got both. William's email is in the chat now. And let's see if this works. Oh, it might be because this service doesn't support Keynote.
I see.
Yeah, if you make it a PDF, can you
Okay.
check if you can present?
Sounds good.
Otherwise, I also can. Yeah, it's just saying that it doesn't support Keynote when I try to
I
do
see.
it.
All right. I have PDF. Is this working? Okay, upload file.
Oh, Alex, could you also put William's slides in? I just sent it on Slack.
Oh, yes.
Thanks. I'm just like, it keeps erroring when I try to do something. I don't know why.
It says processing.
Okay. Yeah. Once it pops up, I think. Yeah, and we'll also post all this stuff afterwards as well too, in like kind of a central place. Okay. Yes, I see it.
Yep.
Perfect.
Nice.
All right.
All right. Yeah, the format will just be, we'll like kind of leave the screen, I guess, so you won't be able to hear us. If you want questions, like you could just pause or just say like, I'll take questions now and we'll come in and answer things from the chat. Otherwise, we might just interject at certain points. But
Okay, sounds good.
All right. Yeah.
All right. Thanks, guys. All right. Thanks for being patient. So hi, everyone. I'm Simran, and today I'm going to share our work on developing simple abstractions for hardware-efficient AI kernel programming. As a brief background, I just finished my PhD at Stanford with Chris Ray, and thanks, Alex, as well for the introduction. All right, so why should we care about this problem of hardware-efficient AI kernels and simple programming abstractions? So as we all know, AI is extremely expensive, and just NVIDIA's Q2 revenue recently, over $47 billion. These models and kernels that we develop are running on clusters of hundreds of millions of GPUs for multiple months across both training and inference. For instance, many of us have probably read, the Llama papers, where we can see like 405B model, 16,000 GPUs, 55 days, something like that, just for training. And more than that, when we try to make one model or one set of operations efficient, we often these days need to completely redo all of that work when a new hardware generation comes out or from a new vendor. So for instance, even flash attention, one of the most widely used kernels and for basically the most widely used AI operation, we had to completely rewrite it going from Ampere to Hopper and then again going from Hopper to Blackwell. And then that's just one hardware vendor. So TLDR, poor software costs billions of dollars worth of compute, and also our AI compute is expensive given that we largely just have one dominant player right now. So in AI, improvements have come from data efficiency, algorithmic efficiency, hardware efficiency, many forms of improvements. But I might go so far as to say that our biggest improvements have come from better hardware and figuring out how to extract more from that hardware. So these are some of the amazing charts from Bill Daly's NVIDIA presentation a few years ago. And the progress of AI has closely tracked the progress of our hardware. So in this talk, I'll give a very brief introduction to AI hardware. I know we just had an intro to CUDA as well, so we'll keep this short. I'll then talk about Thunderkittens, which is a tile-based programming language for AI kernels. And then I will talk about what we've kind of learned from Thunderkittens in terms of how we can start building AI model architectures from the hardware up. in AI, there's a strong legacy of going after, quality first and theoretically driven AI modeling and hardware architecture improvements. But what about if we say, what is the best AI model that might run on this particular hardware, kind of going in that reverse direction? And I'll shed a little bit of light on what we learned there. And finally, I'll talk about a couple key directions going forward. All right, so very basic, starting point, getting on the same page. We have here the simplest possible processor. So what happens is a processor executes instructions using different threads or executors. An instruction modifies the computer's execution state. So you can see here a bunch of different registers that are sort of tracking the state of the program of values, variables used as inputs and outputs to operations. And we have here something called a fetch and decode block that's sort of determining which instructions to run next. And finally, an ALU execution unit, which actually performs the operations that are indicated by the instruction and which might modify the processor's registers or computer memory. But as we are working in AI with hundreds of gigabytes worth of models parameters and KV caches and so on, that's far exceeding the amount of space we have available in the register file or this execution state space. So we often connect our processors to a large amount of memory or data. And memory is organized as an array of bytes, each identified by its address in memory. So the latency to go and retrieve the information that we need from memory, put it into our registers or execution state to then be able to go and run computation can be quite slow. And so memory is often organized as a cache or as a hierarchical formation where there are small amounts of really fast to access memory and larger amounts of slower to access memory. And this just simply follows, simple physics that you would learn in like high school, where if I have a processor, I have a small radius around it and small area, small volume around it. And the closer I am, the faster it is to access. And so that's, our small top of this memory hierarchy here. And the farther away we go, the more space, the more area we have, but the longer it takes to reach that memory. So this is the simple idea of caching. When we look at a new hardware platform and evaluate it, we typically talk about its performance measures in three parts. So memory bandwidth, or the number of items that can be moved to or from a processor from memory per second. Compute bandwidth, or the floating point operations that can complete on a processor per second. Communication bandwidth, or the bytes that can be moved to or from other devices per second. And note, again, that these are hardware, not software, not kernel, not algorithm properties. Okay, so with this shared understanding, let's take a look at a real chip, a real GPU here. So this is NVIDIA's Hopper GPU, or the stylized diagram that they often provide in their marketing materials. And this is just a physical layout of the chip that we can start by taking a look at. So first we can see these colored dots, and I think the prior talk also kind of walked you through this image. And these are the core streaming multiprocessors. So now going from our simplified single processor that I showed you, here we have something like 132 different streaming processors that are operating together on this GPU grid. And on this per streaming processor, we have different threads that are operating together to compute our work, do our work on this processor. And we have tens of thousands of threads operating together on a given GPU, organized in a hierarchy. So around the processors, we can see a couple of other things here in this image already. So we can see memory. This going back to this memory hierarchy where we have small amounts of fast access memory and large amounts of slow access memory. We can see spatially, very close to the streaming multiprocessors, we have something called an L2 cache, which is corresponding to sort of this orange part of the triangle here, which is in the medium range of fast to access and medium range of how large it is. And going farther away, we have these black rectangular blocks, and these are slow to access, but much, much larger. So 80 gigabytes, 3 terabytes per second on an H100 GPU. And the rest of this picture here is components that are used for managing the currents, so inductors, capacitors, power staging. Right. So let's zoom into a given streaming multiprocessor here. And again, this is just for the NVIDIA hardware. So in my simplified diagram, we had simply an ALU, one type of processor. When we zoom into a streaming multiprocessor, we can see that it's extremely heterogeneous. So there's compute pipelines for integer, floating point, double precision operations. There's something here called the tensor core. There's these LDST units for loading and storing related computations, and then the special functional unit for different mathematical operations. We can also see, as we zoom in here, that register file, which was the fastest but smallest part of the memory hierarchy, as well as sort of shared memory, which was that second tier of the hierarchy. Okay. And each of these heterogeneous units, when we go back to those hardware performance measures that I talked about, performs quite differently. So using, again, NVIDIA H100 as a reference point here, that special functional unit, this sort of maroon colored block that I showed, which is for mathematical functions like exp, operates at something like 7.5 teraflops, or the FMA units at 60 teraflops, or those tensor cores at 989 teraflops, or nearly 1 petaflop. And so a basic rule of thumb when we think about these GPUs is that essentially the GPU runs at 100% utilization when the tensor cores are running, and 0% when they're not. Really, the point here is that those tensor core units are by far the fastest available compute we have on these processors. So over the years, these tensor cores, and again, a tensor core is the part of the GPU that's specialized to run matrix multiplication, has gotten far, far faster over the next fastest compute on the GPU, generation on generation of this hardware. So that's really where a lot of this effort is being invested. On latest generation GPUs, it's 16x faster than the next fastest compute in BF16 precision. So again, essentially there's one rule in AI algorithm development, and when we design our AI algorithms, we want to just keep the tensor cores fed. All the compute is there. The challenge of that simple single golden rule is all of the work that's required to make that happen. So in AI, we have large tensors of data, obviously. So if I'm thinking again of Meta's Llama 405B model with up to 16,000 by 50,000 dimensional tensors for different parts of the model there in BF16, this far exceeds the what we can store in these faster levels of the memory hierarchy. And so what really needs to happen is we need to pay attention to how data is laid out across different threads. We need to take these large tensors of memory that we have in AI and tile and chunk them up and make sure that we're only running computation on, we can only run computation on certain chunks or subsets of that tensor at any given point in time. And also, we're not only running matrix multiplications on tensor cores. We do have normalizations, reductions, different additions, and element-wise operations in machine learning that we also need to care about. And so the hard part of AI kernel development is just minimizing the latencies of all of these non-tensor core operations. Again, memory and different types of math. Right. So as we go through the rest of this, I'll talk about kind of the challenges in a little bit more detail that arise as we think about the different levels of GPU parallelism that arise. And then after that, I will go back into Thunder Kittens to talk about how we kind of simplify the process of thinking about each of these challenges. So again, starting off, tens of thousands of threads are running together on the overall GPU. But really, these threads are grouped into small collections of, say, 32 or 64 threads per warp or per wave on AMD GPUs. And these waves are running these instructions together in lockstep. And a big challenge here is for us to think about how the ownership of logical data elements that we care about is going to map to physical thread ownership. So each of these threads that are working together is going to perform computation on some subset of our tile or tensor in our AI algorithm that we care about. And that mapping of which thread owns which element is actually very complicated, which I'll dive into a little bit more. Okay, and then above that warp level of operation, we have many warps that are working together to perform some subset of our overall AI kernel or program. And at this level of parallelism, we really need to care about how we are splitting different warps to use the different parts of the, with the PDF, it's, I guess I should wait to move the slides. We need to care about how different warps are assigned to use each of the different execution units on our GPU. If any particular execution unit is trying to be used by too many of these threads, too many of these warps, it becomes saturated because each execution unit has a limited amount of bandwidth, as we discussed. And so, modern GPUs have a huge number of different asynchronous mechanisms as well that they expose to the user to allow these warps to kind of perform different types of work on different types of these execution units at a given point in time. And unfortunately for us as kernel writers, most of those asynchronous mechanisms are actually useful, so we need to sort of know how they work. One is this concept of occupancy, where we can have collocation of many warps of software. So we can have hyperthreading or collocation of many warps of software threads on the same execution hardware. We can have occupancy or have different types of different waves, different warps go and use different execution units simultaneously to increase throughput. We also have asynchronous loads from sort of Ampere onwards and also equivalents on the AMD hardware, where one can launch a load directly into shared memory, skipping registers, and sort of check for completion of those loads later. We can also have sort of asynchronous address generation using the tensor memory pipelines, acceleration pipelines on H100s, Hoppers onwards. And we can have asynchronous stores and reductions, also using the tensor memory accelerator TMA pipelines. And we also can have different asynchronous matrix multiplications on modern GPUs, where many threads are collaboratively launching asynchronous matrix multiplies directly from shared memory. So the point being here is that there are many, many mechanisms of asynchrony and how we can split up what different warps are doing to maximize our throughput, hide latencies, make sure we're focused on using tensor cores as much as possible. And thinking about all of these opportunities, how to assemble them to build high performance kernels is quite challenging given this landscape of options. Kind of building on this idea of occupancy or having different waves use different parts of the hardware is this idea of sort of wave specialization that's very popular, where we can actually have different waves only focused on doing particular types of our kernel. So we can have certain warps or waves that are only going to do loads and stores between slow and faster memory. And we can have other dedicated warps that are only going to do computation or fast memory movements. And this is kind of called, other words for this is called like a producer-consumer paradigm. And this might be even more advanced than what we were looking at before, because now we can have maybe the workers that don't actually, the workers start to need different resources out of the GPU. So the GPU has very limited resources, in particular, you can see here the registers, which are very fast. There's a very limited number of them. But if these purple kittens here, these load and store workers, don't actually ever need to use any of those registers because they're only operating between this slow and HBM and shared memory, they can actually go and maybe give their registers to the compute workers so that the compute workers can start operating with larger tile sizes and doing their work more effectively. So this is another opportunity to consider here. Okay, so popping up to the next level, so we have these thread blocks, groups of warps that are performing some subset of our parallel AI algorithm, and then and they're running on these streaming multiprocessors or these colored dots. And then overall across the entire grid of different streaming multiprocessors that we have, we're going to have a scheduler that goes and assigns these different thread blocks to the different streaming multiprocessors to perform the work. And for these thread blocks, there's actually a block launch cost and a block teardown cost as you clean up sort of the state of that thread block. And as you're really thinking about super peak performance, these kind of latencies and launch and teardown costs start to rear their heads. And on the same level here, beyond individual blocks, which you can think of maybe as a particular head of attention computation or a block doing maybe a particular output tile of a gem computation, in machine learning, we're performing many different types of operations. So end-to-end transformer, you'll have normalization, positional encodings, MLPs, and sorry, is this slide showing the correct slide? Yeah, maybe I'm just seeing the live stream is looking like it's on a slide ahead, but okay. So yeah, so we have different types of operations in our end-to-end model, and launching these different operations also incurs some kernel launch and kernel teardown time. So between running the attention kernel and tearing that down, or between running the MLP kernel and tearing that down. And these kernel boundaries also are sort of, artificial. So if a certain subset of our streaming multiprocessors is done with a kernel, it just has to sort of sit there and do nothing until all the streaming multiprocessors finish running that kernel before any of the processors can start running the next kernel for our end-to-end AI, training or inference. Okay, so looking at this slide, next slide here, we can see just an example of what I was saying, where we have an ML model with many different layers, many different operations. And these are example kernel boundaries that you might see, for instance, when you're running Llama 1B on a GPU, where you have maybe a kernel for RMS norm, a kernel for matmuls for attention, you have your rope rotary embeddings, you have attention, and so on. And so this is a bit restrictive, and it might not be immediately obvious why. So I gave you one example where the streaming multiprocessors can't go and start running the next work as soon as they're able to. They have to wait for everyone to sort of finish this QKV matmul or finish the rope or finish the attention before any of them can start the next operation. But to give you one example of how, if we didn't have these kernel boundaries, we might be able to do something more interesting, is when our streaming multiprocessors are doing QKV matmul and they finish sort of the output computation for a particular head, some of those processors can go start running attention right away. Or when we're doing this RMS norm here, while some processors are finishing computing that activation, we can start preloading the MLP weights, which are actually very large for these models, into GPU fast memory while some processors are still finishing the norm computation. So if we could break these kernel boundaries across the grid, it offers a lot more scheduling flexibility. But again, thinking about all of this is really hard for the development experience. And finally, in AI these days, obviously we're kind of moving towards, or we're operating on the scale of thousands of GPUs together. And so the multi-GPU communication is of critical importance, and thinking about what we do over scale up and scale out networks. Okay, so With that overview, I will focus on the next part on talking about what we've done in Thunderkittens to try to alleviate some of the complexity in navigating this design space and sort of provide a minimal set of abstractions that one could think about while still having enough flexibility to achieve peak performance on a breadth of AI kernels. Okay, so again, why this is important, just to hammer home, is a critical problem in AI has been mapping all of the AI algorithms and architectures we come up with to run effectively on hardware. And I talked a little bit about the difficulties with even attention before, but concretely, going from sort of flash attention to flash attention for the Hopper GPUs, the original flash attention implementation degraded sort of 47% in TFLOPs, or the utilization it was seeing when we took the kernel designed around the A100s and went to evaluate it on the H100s. And it took 2 years from the release of the H100 GPU by NVIDIA to actually obtain performant kernels with flash attention 3 and sort of the Thunderkittens releases of newer flash attention kernels. So it's been difficult to obtain peak performance for transformers, let alone new architectures. But a major question right now is whether we can replace transformers with improved alternatives, or how can we achieve transformer level quality with cheaper versions. And as we explore, how do we get better quality, or how do we get better efficiency, each of these different types of architectural ideas that we've been after requires kind of paying attention to how efficiently our ideas will run on the hardware that we're using. But just to hammer home the challenge here, when we kind of take a look at some of the popular candidates of efficient architectures that have been proposed over the years and designed with sort of efficiency in mind, trying to be more efficient in terms of memory and compute costs compared to transformers, we can see that designing around theoretical efficiency, or designing architectures that use maybe asymptotically less memory and compute than transformers, in theory, has not always led to architectures that actually run faster than transformers in wall clock speeds on hardware. And so there's this big gap here between kind of thinking about this AI theoretical efficiency and wall clock efficiency. And part of the goal with Thunderkittens is to help address some of that gap and make it easier for AI researchers to quickly prototype on new ideas and understand what the hardware prefers. Okay. So to make the research question precise and just hammer it home with Thunderkittens, again, the goal was how concise a set of programming abstractions can we use to support fast, simple kernels for a breadth of AI workloads. Okay. So here on the kernel side, what do people actually use to write the peak performance kernels right now? So we have a couple of different strategies for, a couple slides here just on laying the landscape of how we might go about kernel programming. The very basic level could be writing raw assembly. So over the past couple of months, have been diving a lot into AMD GPUs, which has been really fun. And a key lesson there is that a lot of the peak performance kernels, for instance, for FA3 or for GEMS, are written in raw assembly. So here you can see 2 traces that I've shown. These are outputs of the ROC profiler if you take the provided AMD kernels and run them through. And you can see these different colors, which sort of correspond to the greens being like matrix multiplications, oranges being shared to register loads, and so on. And there's extremely fine-grained interleaving of many different types of heterogeneous instructions. And each of the rows here corresponds to what a particular warp is running in a thread block. So you can see the warps are just sort of jumping all over the place, doing a mix of matrix multiplies, loads, and vector ops, and all these different colors. Programming at that really fine-grained interleaved level is high performance, but obviously quite difficult and slow and limited to a few experts here. We can also see here some of the SAS or the machine code from NVIDIA, an NVIDIA Flash Attention 3 kernel, so the main Flash Attention 3 kernel. And you can see here that we have sort of fine-grained SAS in assembly. We have like kind of really interleaved fine-grained regular patterns. So I guess the point of what you can see in the FA3 Cutlass SAS is that there are these like regular patterns that keep appearing again and again. So we have F2FP and we have this FMUL and we have that repeated over and over and over again. And so when we have these repeated regular patterns, it might help lead us to think like, oh, we should be using larger programming primitives and capture this regularity and move up a level of abstraction from thinking about this like fine-grained interleaving of these individual operations. Another type of strategy that's used, so here on the right, we have a snippet of code from Mojo's Modular's sort of AMD gem code on an MI300X AMD GPU. And here it's implementing a gem, and they use at the bottom, you can see something called scheduling hints. So the idea here is that the programmer doesn't actually really think about any of the, like write down the assembly or write down instructions in a fine-grained interleaved format, but instead provides hints to the scheduler to interleave the operations in particular ways. And so there's this whole spectrum of how we might be able to program. We could provide compiler hints, we could use assembly, we could write really fine-grained HIP or CUDA instructions. But I think the takeaway here is we want something that's fast, repeatable, extensible to the breadth of AI workloads we care about, and uses as large a set of basic tiles or basic data types as possible to abstract out these fine-grained details. So, really the question here is, where should we set the programming boundaries between sort of, writing in C++, writing in assembly, inline assembly, using these compilers, and then on top of all these building blocks, writing down our kernel schedules, things like producer consumer, or these, aggressive kernel fusion, things like mega kernels. And also, as we come up with these programming abstractions, what insights will scale to our multi-silicon future? So right now, NVIDIA is largely dominant, but we have Cerebras and Etched and Samba Nova, AMD, and Trainium, many different types of GPUs, and we'd like to really be able to take advantage of all of them. So looking at the landscape holistically here, we have basically on one end of the spectrum, so kind of recapping before we go into Thunder Kittens, why is it hard to write these hardware-aware AI kernels? And why has there been this gap between theoretical efficiency and wall clock efficiency as we iterate on these new like AI architectures, AI algorithms? The first main challenge has been that some of the architectural choices that we make are not actually compatible with what the hardware prefers. So for instance, some of the architectures that are efficient in theory don't actually use the tensor cores or those matrix multiply units, which is just a big loss in performance. And some of the architectural choices require really unstructured memory accesses and are not really hardware friendly as we think about the need to have sort of coalesced and large loads. The other main challenge has been that of the tooling and the software support. So just to look at the two axes here, we're going to think about what is the peak performance that we can elicit out of our GPU when using programming abstractions on the y-axis, and on the x-axis, what is sort of the simplicity and usability for AI researchers. So on the far right, we have things like PyTorch or TensorFlow or Torch Compile, which is the way in which AI researchers go and write down their new algorithms, new architectural ideas, and iterate and understand the quality. And these are very familiar to the AI audience. So in similar spirit, using a Pythonic interface, there's Triton from OpenAI, which is very, very widely used. And it provides a lower level access to the actual memory hierarchy of the GPU and to being able to specify these AI kernels. And so it has that nice ground of being simple and usable and Pythonic, but at the same time, by providing the simplicity, the level that was chosen by Triton originally when we did this work was not sufficient enough to elicit peak performance out of the hardware. So for instance, Triton did not offer the ability to control what was stored in register memory or that top level of the memory hierarchy, and also didn't really provide the mechanisms to specify fine-grained asynchronous kernels and execution strategies that we would want. Obviously, these days we have linear layouts and gluon and new techniques here, but this is sort of what we were looking at when we started the Thunder Kittens work. And on the other end of the spectrum, we have, again, assembly or writing CUDA and HIP in C++, or abstractions, which are deeply nested C++ templates over CUDA and HIP with cutless and composable kernels. But those latter two, despite providing some semblance of abstractions, are not very Pythonic, not very aligned with how AI researchers like to go about doing their work in PyTorch style frameworks, and use kind of these deeply nested C++ templates, which are hard to think about. And that latter point is more opinion and also kind of talking to many people who try to write these kernels. So with Thunder Kittens, we provided this framework that, studying the question of what is the sort of minimal set of abstractions resulted in Thunder Kittens, which is a DSL to achieve simplicity and speed for a breadth of AI kernels. And I guess a very poor proxy for simplicity, we have sort of like lines of code in the library here. It's just 4 folders. We tried to keep it very, very lean. If you kind of go into the repo and look, it's sort of tries to be as transparent about what's going on with the hardware and what each of the abstractions is trying to do. So mimicking our discussion of the challenges at each level of GPU parallelism, I'll tell you a little bit about the abstractions that have gone into Thunder Kittens to help alleviate some of the challenges I discussed. So at the base level, when I talked about this problem of warps are working together, they each need to own different data elements and process it. And that challenge of managing which threads own which parts of our data, these memory layout challenges, what Thunder Kittens does is it specifies a base 16 by 16 tile as its core data type, which is philosophically trying to be very much like programming with tensors in PyTorch. All of the details and complexities of the memory management of which threads own which parts of that tile, we try to abstract away from the user and automatically select those memory layout decisions to be as compatible with what the hardware prefers as possible. So the reason that we pick 16 by 16 tiles in this original version of Thunder Kittens is because the underlying HMMA SAS instruction that we were looking at on the NVIDIA side of things was a 16 by 8 by 16 matrix multiplication as that base intrinsic for NVIDIA. And I'm seeing here a question on the chat that's, how different is HIP from CUDA in terms of programming and syntax? And both of them are very, very, similar. You can basically HIPify your CUDA code very quickly and it works pretty well. But the actual details about what the tensor core instructions look like, what the memory movement capabilities we have and so on look quite different. And why I bring this up here is that I just mentioned, the 16 by 16 tile size is picked because the underlying HMMA instruction on NVIDIA, but on the AMD GPUs, we have many different and sometimes smaller tensor core shapes that we're going to be using. And depending on the MI300, MI325, MI355 platform that we're using, different tensor core instructions that we want to be using. And so the tile size here is really meant to be kind of co-designed with what that base instruction that you're going to be using is. What's the base size of that matrix multiply unit? But it's really designed around that tensor core. And I'll tell you a little bit about more about that in the next slides. So if we think about memory and register memory, shared memory, global memory, tensor cores at the, when we're thinking around like, okay, our goal is to be using these tensor cores require very, very particular register memory layouts. So when that instruction, the tensor core instruction, is called collaboratively by a group of threads, it expects that certain threads own certain parts of the input matrices to the matrix multiplication. So in, forgot to switch side. In black here, we have an AMD A matrix register layout for a 16 by 16 by 16 BF16 instruction. And in yellow here, I've denoted what parts of the matrix this A matrix thread 0 owns, in pink thread 1, in green threads, I think 16, and red thread 17. On the far right here, I'm showing you an example from NVIDIA's BF16 A matrix register layout. And you can see that the positions of which thread owns which part of that A matrix looks quite different on these different GPUs. But that's like our top level constraint. So really in Thunder Kittens, we tried to make our register layouts eager. In other words, pre-assign the thread ownership to be compatible with what the tensor core instruction is going to expect that thread to own. And this has cascading implications going down to shared memory and global memory layouts. So on the other end from global memory, the hardware is really encouraging us to use large coalesced aligned global to shared memory loads. Large, to minimize instruction issue latencies, and then coalesced aligned are what's hardware friendly and what's sort of like implemented in terms of the strides there. In between global memory, where we want these large coalesced aligned loads, and register memory, where we have these really particular constraints about which thread owns which element, we are often going through the intermediate parts of our memory hierarchy, or shared memory. And shared memory is designed in a way that's banked. Or in other words, that shared memory space is broken into, say, 32 or 64 chunks that can simultaneously serve memory to threads. And banking is really nice because it can help us, get high throughput and serve multiple pieces of data at a time. The challenge is that if multiple threads try to access the same bank at the same time, their memory accesses will get sequentialized and really hurt our overall kernel performance. And so that challenge of how we should actually represent data in shared memory in order to both let threads use those eager register layouts and at the same time make sure that we're using large coalesced aligned global memory loads is quite annoying and challenging to think about. And so the granularity of those global loads and the register layouts will also govern our ability to avoid bank conflicts and tell us like how flexible we can be in even getting rid of all of those bank conflicts or occasions when multiple threads are requesting memory from the same bank. Let me walk you through one example of where this could be a challenge concretely from our experience working on the AMD GPUs. So recently, a wonderful master's student at Stanford, Will, and I have been looking at these problems. And we have here this FP, like looking at how we can do FP6 gem instructions on MI355X. So one of the challenges we sort of faced was on this machine, you really want to be loading in 4 banks of data at a time, or 16 bytes of data. And on the register side, for the tensor core instructions, each thread needs to own 6 banks worth of data. So if we're loading in at 4 banks of data on the global side and requiring each thread to access 6 banks of data on the register side, I won't go into all of the details, but you can see that there's sort of this misalignment in terms of those granularities here. And it becomes really, really hard to avoid bank conflicts because we can't fully control where all of those global loads are going in shared memory space in a way that we can maximally avoid thread sort of conflicts when they're pulling shared memory into registers. So overall, these memory layout challenges, I hope I've convinced you, are really challenging, and this is why it's very, very nice that Thunder Kittens has kind of distilled the core principles for how to pick these layout decisions and abstracted them away from the user, where a user kind of just says, I want this register tile, I want this shared memory tile, and these decisions are taken care of. Apologies, I guess I'm used to using my keynote, but this is the slide that I meant to show for that part. So on the right here, you can see in blue for thread 0 through 15, it's requiring to own 6 banks. So these are banks worth of data in order to use the tensor core instructions, but our global to shared memory loads are at 4 bank granularities. So for 2 of the strips here marked in red, we sort of get these bank conflict issues. Okay, so moving on to the next piece here in Thunder Kittens, once we have these basic tile building blocks, we'll realize we want to run operations over them. And so again, following our desire to be as familiar to AI researchers as possible, we pulled our abstractions from PyTorch and NumPy's library functions. So we can apply things like an MMA or mapmul over tiles that we've defined. You can see exps here, loads and stores, obviously, zeroing things out, or ones, or different reductions, or subtracting rows from tensors and so on, vectors from tensors and so on. And once, so the way in which we've defined these different functions under the hood is in a highly templated way. So if you take a look at one of the kind of core files in the Thunder Kittens repo for some of these instructions, you can see that we define these core templates, for instance, for tile maps or tile reductions. And that makes it very, very easy to add any additional operations that you care about. For instance, adding 2 tiles, subtracting 2 tiles, multiplying 2 tiles, dividing 2 tiles can all kind of wrap the same underlying instruction templates. And this has helped us kind of, with code cleanliness and making things as easy to understand as possible. And the other important thing to note here is that these Thunder Kittens functions are designed to have no side effects. So TK is almost an ISA. All functions sort of take this form of function with a destination, source 1 and source 2 input parameters. And we're basically just wrapping sort of like PTX or assembly instructions for the most part, as much as possible here. And an additional important design decision was that Thunder Kittens is written in HIP or in CUDA. So this means that it fails gracefully. If a new hardware platform comes out, like say Blackwell comes out, or a new set of functions is required that is not yet supported in the TK function library, we wanted developers to be able to quickly write their own inline functions in CUDA and HIP as soon as possible with no sort of delay waiting for some upstream company to update the repository. So we really wanted Thunder Kittens to fail gracefully there. And emphasizing that point, sort of when Blackwell came out, some of my collaborators on all this work, Ben and Dan Fu and folks implemented Blackwell in the span of, say, like 2 days, which was very exciting. Okay. At the next level of the hierarchy here, at the block level, Thunder Kittens provides a general kernel template for coordinating asynchronous execution across warps in a thread block. And we have a template that's sort of built on the producer-consumer paradigm where we take care of deciding, which workers, which warps are going to go and do loading and storing, which ones are going to do compute, and how do we manage the synchronization between those subsets of workers. What this template does is basically reduce the developer's effort to populating a few boilerplate functions within this model. So very similar to when you use nn.module in PyTorch and need to fill in an init function or a forwards pass, our goal was to try to have a boilerplate load function and compute function and store function that says what needs to be stored in this kernel, what needs to be loaded, what needs to be computed, and then the orchestration of warps and synchronization around executing these boilerplate functions is taken care of on the TK side, similar to how AutoGrad is there on the PyTorch side. And we provide levers to tune this template. So how many warps are going to be working together in the template, or how large of sort of buffers of memory might be able to exist between the different partitions of workers that we have executing this template in order to minimize synchronization. This is a toy example of that tuning process in action. So here for our attention just simple flash attention to style kernel in Thunder Kittens implemented within the template, you can kind of tune the number of consumer warp groups that are working and the number of stages that are going in being between our producer and consumer work groups, and you can see how you can tune the T-flops and performance of our overall kernel by toggling these simple integers that parameterize the template. Depending on the hardware platform that you're using producer consumer, using this sort of worker specialization versus using more occupancy style techniques will differ, but the idea in Thunderkins is we've been building these little prototypes or templates that can abstract out those general data flow schedules because we've observed that you can kind of use the same ones again and again for a particular hardware platform. So on the Hoppers, on the Blackwells, this type of wave specialization is really what you always want to be doing. We see that across a breadth of workloads. On the AMD machines, it looks pretty different in terms of the type of schedule that we find, but we find that once we've picked a particular schedule, it's pretty robust across different workloads on that hardware platform. And then at the next level of the parallelism hierarchy here for the grid level, thread block launch, thread block teardown that I mentioned earlier in the talk, the kernel templates that we've provided use a persistent a kernel approach where you can just have new work being pulled by these thread blocks over time as they finish earlier chunks of work. I think also mentioned a little bit in the last talk, that process of scheduling tasks or scheduling what thread blocks are doing on these different SMs is very, very important. So the block order of how overall, say, gem or attention work is being done really affects our ability to reuse parts of our cache in our memory hierarchy. And being able to effectively reuse cache memory can dramatically affect performance. So at this level here, we provide sufficient control to be able to control that block launch order within our persistent grid in our kernel template. And finally here at the final level that I mentioned, in the challenges section where we want to be able to fuse and remove these artificial kernel boundaries in work led by my lab mates here, Ben and Jordan, that I was helping advise. We were looking at kind of running end-to-end Llama 1B or Llama 70B and so on within an entire kernel here. And so you can see that when you are able to eliminate these kernel launch boundaries and take advantage of all the fine-grained scheduling opportunities, you can achieve quite impressive performance over widely used and well-optimized engineering efforts like VLLM and SGLang for decoding throughput. So yeah, and shout out here to Ben and Jordan. You should reach out to them if interested. We're continuing to kind of think about the right abstractions here. Okay, so at the beginning of the section, I mentioned, the question, how concise a set of programming abstractions can we use to support fast, simple kernels for a breadth of AI workloads? How did we evaluate this? So recapping the principles of Thunder Kittens, we observed that AI workloads follow a few patterns, and Thunder Kittens can use a small number of primitives for programming our kernels. We wanted our primitives to be transparent to the underlying hardware. And we wanted to restrict the set of primitives to those that yield high performance. So sometimes there are nice functions that you wish you had when writing a kernel sort of lazily, but we try to eliminate those from the library to make sure that we can guide developers on the right path. And in the evaluations, we looked at kind of implementing a breadth of workloads, so convolutions, subquadratic architectures, linear attention, state space models, gems in different precisions, attention, and memory-bound kernels, so or positional encodings and normalizations, and so on, across a variety of hardware platforms. And we're interested in what sorts of speeds we could get out, as well as how simple the code looked and felt. And so how often we were reusing the same underlying TK function building blocks, and a poor proxy that I've put here, but lines of code. And we kind of found that with our approach, we could use drastically fewer lines of code than the higher complexity CUDA, HIP, Cutlass, composable kernel style approaches, while matching or performance and being competitive. And we could use comparable lines of code to the simpler frameworks like Triton, while sometimes outperforming the performance that you could achieve there by massive margins. Through this project over time, we've been kind of stress testing our core philosophy and ideas across different hardware platforms. So even here in the numbers, I've shown H100, 4090, Apple, there's like Blackwell support, Apple, we're working with folks at Intel, AMD, Revos. So it's been quite exciting to see these ideas generalize. Okay, so for the overall, where this is sort of gone right now is like we're really trying to continue supporting this in the open source. We've been excited to get contributions from a bunch of folks, including the GPU mode community, and would love to keep working with you all and getting feedback and understanding how to improve these ideas. You can use Thunder Kittens as part of GPU mode's kernel competitions, which is really exciting. I think there's a new AMD one also released recently. It'd be fun to get support there. And we have presented this work at iClear recently, and been excited to see the Thunder Kittens framework used in a bunch of published work by different universities over the past few months. In industry, Thunder Kittens is currently used at Cursor, Cruise, Jump Trading, and Together AI to write custom production kernels. And also, most importantly, the goal here was to kind of simplify this experience of writing kernels, especially for a bunch of us in our lab at here at Hazy, where we're really interested in these new architectures. So we've been excited to see collectively in the community a bunch of approaches towards this goal. So Thunder Kittens itself drew inspiration from many different prior works and a long history of ideas in high performance computing, parallel programming, and including, I want to shout out, Triton, Halide, Cutlass, Flash Attention, all of that work was heavily inspirational. And in the past, sort of year or so since we released Thunder Kittens first in May 2024, we've also seen a lot more of these Python-like DSLs for high performance kernel writing. So I think that, this problem is being addressed in a variety of ways, which has been great. Okay. So that tells you a little bit about Thunder Kittens. I'll briefly tell you about one example of how we use this framework to bring back new AI capabilities and kind of look at the architecture space for new AI models as well. So as we go into this, here's our basic familiar attention equation, where we have expensive memory complexity that scales linearly in sequence length, and compute complexity that scales quadratically in sequence length, making it hard to achieve some of our long context capabilities that we care about. So attention, again, the equation is y equals softmax qk transpose here times v. And here we have the softmax over this QKT matrix. This QKT matrix is an n squared sized matrix, and we apply the softmax over that. So again, this memory complexity scales linearly in sequence length, compute quadratically. So when we're thinking about memory with a transformer, the KV cache is what is the real cause of this, what is causing this linear memory complexity. And the KV cache for a 128K long sequence of tokens can be something like 8,400 gigabytes. In contrast, Llama 70B parameters is like 140 gigabytes. So these KV caches for individual sequences that we care about processing start to approach the memory consumption of our model altogether. So it's a massive issue in machine learning. And you can see here that there's a close relationship between the size of this KV cache with the memory consumption of our attention transformer architecture and the throughput or tokens per second of experience that we can get when interacting with these models. So as a result, one popular idea from 2020 and earlier, been a bunch of work here, is to, instead of using this softmax equation, take this attention equation and instead use these feature map functions that are independently applied to the queries and to those keys transposed. So here we have this feature map function phi that you can see we have phi of q, phi of k transpose. And what is specifically nice about using this instead of the softmax, standard softmax attention, is that we can reorder our matrix multiplies to reduce the memory and compute complexity of our computation. So here, what we can actually end up doing as we produce our different yi out of this linearized form of attention is that we can multiply the keys and values first, whereas for softmax qkt, we need to multiply the queries and keys first before we can go and apply that softmax equation. So by decoupling these feature maps rather than that softmax applied collectively to q and k, we can change the order of these computations. So when we go and multiply keys and values first, we get a memory complexity that's d by f, where f is the dimension of the output of our feature map. And our compute complexity becomes linear in sequence length. All right. But a key question is how we should actually choose that feature map function to balance quality and efficiency here. So if we look at this feature map equation, if f is equal to n, then the memory complexity becomes n by d and compute becomes n squared by d, which is exactly the same as we got out of vanilla softmax attention. If f is a lot smaller, we get much more efficiency out. But hopefully intuitively, there's a trade-off in machine learning. There's this information bottleneck. If we use very, very small amounts of memory, it becomes hard to remember everything that is going on in our sequence that we're processing, and we get sort of quality degradation. So there's this quality and efficiency trade-off that's hopefully somewhat intuitive. So going back to Thunder Kittens, we wanted to kind of see, what is the sort of, in some sense, choice of these linear attention feature maps that the hardware might prefer. And this exploration resulted in something called the based linear attention architecture that we proposed. And what was really exciting about this was we could start to get really, really high T-flop numbers and utilization numbers out across a variety of sequence lengths while using pretty large state size, pretty large amount, like reasonably large amounts of memory with our feature map choice. To kind of sort of balance this quality and efficiency trade-off space. So with Thunder Kittens, we explored different forms of like this hedgehog linear attention. We tried optimizing Mamba. We worked on this based linear attention. And what was really exciting about based is it's really designed around properties that are present in Hopper and going forward. So leveraging the WGMMA and also by design kind of requiring a small amount of data movement between global and shared memory and doing a lot of the kind of state expansion and artificially growing that feature map dimension F on data that's already in fast shared and register memory. So kind of by co-designing this linear attention with the hardware features in mind and from our experience with Thunder Kittens, it allowed us to more effectively balance quality and efficiency here. I showed earlier this contrast between the plots of memory consumption on the x-axis and quality on the y-axis, and how it's been hard to kind of map that theoretical efficiency to wall clock efficiency. Here we were really excited to see at the time, there are popular architectures out there, Hyena, H3 Mamba. We could start to expand architectures to use 8 times the memory of some of these prior models that had been proposed while running at 5x the hardware utilization of some of those prior architectures as well on these Hopper++ GPUs. Okay, so and with that, kind of on that section of what architectures the hardware prefer, I'll wrap up with a few key directions that I think are quite exciting going forward. So one, I think there is a lot more work to be done around these directions of theoretical versus hardware efficiency perspectives. So is my slide changing? Yeah. Over the generations of, over the years, we've been kind of closing the gaps between attention and these efficient alternatives and finding ways to build techniques that go beyond the quality we can get with vanilla attention as well. I think we have a lot more work to do in terms of understanding which modeling choices the hardware prefers. We've done a lot of work on kind of what pushes quality and what theoretically pushes quality. But when you start with a particular hardware platform or a particular type of workload, like low latency or high throughput by design, can we start from the hardware first and design from that direction? And kind of shedding light on what we've seen in our work is that this has really caught on. So I think with the based architecture in particular, where we designed really around using tensor cores, using latest generation features on the most advanced modern GPUs, a bunch of the techniques in the based work were kind of adopted and carried forward into various popular models subsequently. So maybe the Mamba architecture that I mentioned was fast in theory, but not really fast in wall clock speeds, or not really taking advantage of tensor cores. Also upgraded to kind of a more linear attention style approach, and you see Minimax here, which is using similar techniques to based and so on. So I think there's a really important direction here in terms of understanding what architectures the hardware prefers. Next, we really care about this kind of multi-silicon future where we're able to use all these different types of AI computing that are coming up. Over time, we've thought a lot about kernels in this talk, but I think the communication and memory bits here are really where there's a lot of interesting work left to be done. So again, game changing on the NVIDIA side, we have these NVL72 sort of super chips where traditionally we think of a node as 8 GPUs together. Here we have 72 GPUs together that are connected via these very fast scale-up networks. And when you want to implement things like expert parallelism, pipeline parallelism, this is the huge advantage because of the sort of gap between scale up and scale out network speeds. And so I think the algorithmic innovation here and how we can even enable fast model training and large scale model training with AMD GPUs and other types of compute that don't have that type of advantage will be a really important problem as we continue. All right, and with that, I will close out. Here's the set of folks that made all of this work possible. So I worked on Thunder Kittens with Ben Spector and Ariane Singhal and Dan Fu and Chris. And then Will here is awesome on the AMD efforts, and Sabri on Based, and a bunch of folks here on mega kernels. So please check out all of these different repositories here and connect with us on GPU Mode. We'd love to hear your feedback and experience using these tools. Thank you.
All right, thank you so much. I think there are some questions in the chat, but Han, if you want to ask yours first, you can.
Well, maybe let's go through the questions in the chat first, and I'll put my question toward the end.
Okay, yeah. So some of them were asked kind of early on, but someone asks basically, do compilers, I'm assuming they mean for whatever platform you use, not automatically fuse different kernels and take care of pipelining data?
Yeah, so CUDA graph is really awesome for a lot of the kind of hiding those kernel launch and teardown costs that I mentioned in earlier slides. So you can take a look at our blog post written about properties there. I think some of the opportunities to sort of decide when do I preload, for instance, I mentioned the example around when a particular head's worth of QKV matmul computation is done, we can start running attention for that head, or around preloading certain MLP weights, those types of opportunities that might be hard just purely with the way the rules that compilers have kind of embedded in them are exciting when you have this like fine-grained control. So I think it's an extremely effective approach, and it does take care of a lot of those kernel launch costs. But we were interested in what we could do kind of on top of that with our own hand-rolled scheduling.
And there were two questions about, I'm assuming this is the figure with like all the different DSLs and libraries. Mm-hmm. What's the position of the Qt DSL with respect to that performance figure? And then also another question is, how about like JAX or Flux?
Yeah, great questions. So Qt DSL, I guess personally, I've mostly read some of the code. Like I think that recent FA4 kernel that came out, that it looks very, very clean. And I think that it looks very promising. So I would say it's made a lot of progress since early 2024 when we started looking at Cutlass, and achieves a lot of these goals. It's Pythonic, it's simple, easier to read. So it's really, really great work. I think it still is more on the NVIDIA. I mean, it is more on the NVIDIA side. And so I think it's interesting to see what kinds of design decisions would change when we want to like also extend to say Apple or AMD GPUs and so on, and like how we can go there. But I think tile-based programming is definitely here to stay and reflected in a bunch of these frameworks now. On the JAX and Flux side, honestly, I don't really use JAX or Flux much, so I don't feel like I have much to comment there.
And then another question is, does TK use NVCC, I guess, under the hood?
We compile it, so it's compiled code. So yeah, we use the NVCC compiler there, like Clang LLVM stuff on the AMD side. The compiler bits are quite interesting. I think like on the NVIDIA side, you don't see as much like instruction reordering and so on when you compile from the code that you've written on the CUDA side or with inline assembly to the SAS. And we find that the compiler is actually pretty, it's able to kind of handle inline PTX very, very well and make optimizations around that. On the AMD side, it's been a bit of a different experience. We find that kind of using a bunch of assembly inline volatiles is more of like black box to the compiler, hard to sort of reorder instructions around that. And there's also opportunities to kind of provide scheduler hints to the compiler as to how to reorder instructions. And so I think the compiler questions here are actually very interesting to think about when we pick like how to build these programming abstractions. But yeah, I think for TK we're using the sort of default compilers there.
And then the last question is, have you explored different partitioning mechanisms of task loads operating on tensor cores to see if different templatizations work better in Thunderkittens?
I'm not sure if I fully grasping the intent of the question, but we definitely see that different types of templates work well on different types of GPUs. So, we'll release more of this work soon, but for instance, on the AMD GPUs, you don't really have features like register reallocation where producers can give their registers to consumers, and things like producer-consumer wave specialization as a result can be very wasteful for registers. And so the types of overall templates that you might want to use can look pretty different across different types of platforms and hardware in general. Yeah. But we considered a bunch of these when coming up with the LCSF template that we put together in Thunderkittens. So yes, I guess we did explore different partitioning mechanisms.
So maybe I'll chime in with two questions on my. So first of all, thanks for very nice presentation. So my first question is, I think one sort of a very different programming model from TK compared to like TVN or like Haley, kind of a different algorithm and scheduling languages. I'm just curious, sort of your take or comments on this very sort of different philosophy of more like straight line compilation versus more heavy scheduling algorithm. Be honest, I'm just curious what's your take on this. And my second question is, one thing that's being challenging for compilers is as chip keep coming up, how can the framework can keep adapting yourself to the newer generation? So I mean, we know TK adapts extremely fast, different newer generation different chips, different hardware. I'm curious what sort of secret sauces that you build early into the framework that make it easy to adapt to different newer generation of hardware.
Yeah, great questions. So on the first one about, we have compilers, we have assembly, we have HIP, CUDA, C++, or Pythonic frameworks, and various levels of abstraction. I sort of think things will move more towards we'll implement schedules and like the patterns of mega kernels or the producer-consumer, the occupancy-based schedules in Pythonic frameworks, and that should be pretty easy because we have core building blocks. I think the building blocks, like the tile data structure, its memory layouts, and so on, it's nice to specify on the CUDA, HIP, C++ side, where that kind of comes into your question of what we decided on the Thunderkitten side that helped it kind of port to new hardware very quickly, is that that's the place where you have flexibility to just grab the new PTX, grab the new CDNA ISA, and like plug it into the library when it comes out, and just kind of plug and play that. And you can build these higher, I guess, coarser grained building blocks like tiles compared to fine grained assembly style interleaving that I showed on the slide when we're operating at this level of abstraction. So I think schedules on the Python side, these building blocks like tiles on the HIP CUDA side. And then I think for the compiler side, you might see, those issues that I mentioned where sometimes inline ASM volatile inline instructions are treated as black box. It's hard to sort of reorder around them. That's a place where I think compiler type hints and they can play a role in kind of doing that rescheduling bit for the user and finding those inter sort of cluster optimizations there. So I think of like the kernel schedule programming in clusters where you have like a collection of loads that that certain waves are doing or warps are doing. You have collections of like compute operations, and kind of once you schedule like which warp is going to do those different clusters, you can have like fine grain interleaving within that, and compilers can help with with that bit. So yeah, I guess schedules, building blocks, and then like within cluster fine-grained interleaving is where I see the role of each of those three.
I see. So actually, maybe a quick follow-up question, which is, I don't know too much on the AMD side, but let's say on the GPU, Ampere to Hopper to Blackwell, etc. Every generation, it seems to be easier, quote unquote, to program, like in sort of a conceptual sense, because NVIDIA keep putting specialized hardware primitive to do every single part of the piece of the puzzle. Do you think going forward, I don't know too much, maybe AMD can be a totally different picture here, but do you imagine the current programming become easier with things like TK, or do you think they'll be more complex as how to orchestrate to call this primitive becomes the more challenging piece?
I think it's going to get easier and easier. So on one extreme, with hardware like etched, if transformers are what we end up with, there will be no need for kernel programming. On the other end, I think we're seeing similar trends catch hold and be used across different types of general purpose hardware like asynchrony or bigger, faster tensor cores. And so as we understand the design space around those central axes, and we'll like come up with principles as a community and make progress there. And then I think the models are also going to get better very quickly at writing kernels. So that will also make things a lot easier. So yeah, definitely will get easier.
Okay, so which means the future job security for us will be not that good, or it gets better because we need to build a framework like this to make this job easier.
Yes, and I mean there will be lots of different types of hardware. So and it's also interesting, obviously, to consider what types of designs don't fit in our current hardware paradigm at all and force us to kind of build entirely new stacks. I think kind of the corollary of my point around building architectures from the hardware up is like, can we break the model that's been provided to us by NVIDIA and AMD and so on, and like show them like, oh, like this is an entirely new thing that you should have been thinking about all along. Yeah.
So maybe the fact you build this whole framework also help you and the team, people to think about what makes sense from the algorithm standpoint, that of view, and also realize sort of the limitation for the hardware, and then your knowledge of the algorithm can sort of hopefully influence the next generation of our design.
Right.
Yeah. Cool. Yeah, that's a good answer. Thanks. I think I see two more quick questions. I think one question from CH is that NVIDIA provides colors, AMD provide composable kernel. They can give good pipeline and hint to compilers. What benefits TK want to compete within?
Yeah, so I talked a little bit about Cutlass and composable kernel on one of the slides. So firstly, I think that TK is more of like art project. Like it's nice that it's being used in development, but mostly it was like kind of around that research question. So I don't think we're necessarily like competing with them. I think they're very production grade, widely used software platforms. But Cutlass and composable kernel, as I've kind of like dig through them and read some of the kernels implemented in them, kind of following the logic of the kernel has been a bit difficult. It kind of tracks through many different files and many different dependencies and like sort of deeply nested templates. And I think the learning curve there it is a little bit harder, but that's, I guess, just opinion. And I think the older versions of Cutlass composable kernel more were oriented. I think we tried to kind of minimize the set of like abstractions that you would need a little bit more. So we have like sort of one kernel template, which is this producer consumer template for the Hopper GPUs, rather than having like an array of many different kernel templates on the Cutlass side. And the composable kernel side doesn't really provide these sort of like tile-based abstractions, is not very clean. But we've taken a close look at all of these, and they're kind of more full-fledged support, but quite unwieldy and not like a good educational entry point for somebody who just wants to know like what's the bare minimum of what I need.
Yeah, thanks. I think in the interest of time, we'll take two last questions that just pop up in the chat. The one question is about the opinion of Mojo. I guess that's relatively in the same sort of vibe. The question about different frameworks, so just your thoughts on Mojo. And the last question is the recent GPU architecture that makes this producer-consumer special kernels work better than occupancy-based kernels does both in one thread. So that's a question.
Yeah. So for Mojo, I've played with it a bit. I did some of the GPU puzzles that they released, and I also, at the beginning of this talk, talked about their MI300 gem kernel. I think Mojo's really, really exciting. It's multi-silicon and very extensible. Sometimes I've had trouble printing things, which I like to do. But beyond that, and some of the error notifications are a bit hard to parse when you make mistakes, but beyond that, I think it's like can get you peak performance. It's like Pythonic, and they have very clean abstraction. So excited to see it continue to grow. For recent GPU architecture, oh yeah. So I think one of them is the register reallocation bit that I mentioned. So if you create a warp and you want it to be a producer that's only doing global to shared memory loads, but it also is using up a lot of your registers, it can be kind of wasteful and create more register pressure. So what's nice on the Hopper GPUs is that you can have dedicated sort of producer warps give their registers to the consumer warps from the shared pool of registers. So that's one. Two, you kind of need sort of these fine-grained synchronization abilities. So you want to only synchronize consumer warps or only synchronize producer warps, or kind of set up these barriers. And so the M barriers on Hopper++, and those are nice, but perhaps you could implement them with shared memory anyways. So I think those are two pieces that you'd want. And then the asynchronous memory pipelines for sure. And sort of sufficient shared memory to have buffers that are deep enough between the producers and consumers for more compute-bound stuff.
Yeah, great. I think that's in the interest of time, I think we'll end the session here. I think there are a couple questions in the chat we don't have the time to get through, but if Simran, if you can leave your contact information, we can pass them to the audience so they can follow up with the questions if they have any.
Sounds good. I will leave my email.
Yeah. Again, thanks Simran for the nice presentation, and also thanks everyone for today's session. I think we have a very nice 2-session GPU kernel program today, which is going to be fun.
Yeah, thank you, Simran. And this concludes the week-long.
Yes. Thank you all for tuning into all these things. All the recordings should be up, and we'll also have the like slightly edited versions up on the channel too, to like avoid all the downtime in between. But yeah, thank you guys for joining.
Yeah, thanks everyone.
Yep.
Oh.